Thank you once again for the opportunity to be part of this conference. This study was part of my PhD work in Ghana, in one of the largest sub-basin, river basin in Ghana. The topic is extreme changes of daily rainfall and temperature patterns in a tropical sub-humid basin. The work is about using the statistical downscaling model, the decision-centric model developed by Professor Wobi in Loughborough University in UK to assess the scale of downscaling extreme climate indices in the basin. And this work was done under the supervision of the co-authors as listed here. A presentation will follow this outline. And first of all, we have now come to accept and also have evidence of the impact of climate changes, especially its extreme events, like the previous presenter was talking about sea level rise. We heard about some of the other impact, but in our own area, the impact is not extreme, as in the damages are not that visible. It's more or less like a slow onset. So mostly they are not that much recognized in the international documentations. And the demand for this weather and climate extreme information is now high, because especially the farmers, those I work with were farmers, they're experiencing these extremes in their activities, and it's causing them to lose value for the inputs they make in their production. And as I said earlier, in our own area, we are experiencing floods. That's more frequent. There are droughts, storms, and heat waves in sub-Saharan Africa, and specifically in the basin, as a River Basin. There's limited knowledge on this in Ghana, especially modeling the impact to help prepare with the development of early warning systems. Currently, we have rainfall forecasting, and farmers are getting the benefit of it. Other studies have looked into the integration of indigenous forecast with the scientific, and farmers are benefiting from those as well. But when it comes to the area of extreme impact, extreme events, there is a little being done. And therefore, we need these things to plan for future events. And currently, we are relying on only global and regional simulations. And studies have shown that these global and regional models does not give details of our local impact in an area, specifically in the river basin or at the local scale. So the aim of this study was to first evaluate if the statistical downscaling model or decentric model developed by Wobe in 2013 is able to simulate rainfall and temperature extreme indices in the basin. The data used for the historical was from 1981 to 2010, and also to project some of the extreme indices that the model was able to simulate, as comparing, evaluating its capacity with the historical data. This is the river basin located in Ghana. It's the largest southwestern basin in Ghana. And this study is very important because this is the hot spot for the production of the two food security crops in Ghana. That is maize and cassava. This is the hotspot where it is produced most. And moreover, this basin is the highest producing area of cocoa or cacao, which is the highest economic crop for Ghana. So it is important to look at how extreme indices will be affecting the climate in the area. And cropping in this area is mainly rain-fed. It's mainly rain-fed. And the changes in climate is actually impacting their activities. First of all, the daily rainfall temperature and minimum and maximum temperature were failed because they were missing data. Actually, the stations, climate stations in the basin were over 200, but only 7 were functional. And were over 20, sorry, 20, but only 7 were functional. Some of them, the data is not up to 10 years. Others had a lot of missing data. But those ones that had missing data that were acceptable between 10%, below 10%, were 7. And that was what was used for this work. And quality control, as well as the extreme climate analysis, were carried out in our ClimeDex, as the R version of the ClimeDex package. And for the rainfall, daily rainfall was set at 200 as a maximum. Upper limit was 200 because the average rainfall, maximum daily rainfall during the major rainfall season was around this figure. For the calibration and validation of the model, mostly the model operates with the stochastic weather generator and the multiple linear regression. In downscaling, that is reconstructing the daily station data based on predictors, the atmospheric parameters, and it works for 366 days. That's how the model was developed. And the atmospheric parameters used were the predictors developed by the National Center for Environmental Prediction. And the data was divided into two using the two-fold cross-validation technique, which is already automated in the model. And the calibration was done with 1981 to 1995 and validated with 1996 to 2010. And these are some of the predictors that were used for the calibration of the models. The calibration was done for each station, and a minimum of 4 predictors were used to calibrate for each station and for each parameter as well. So rainfall was done differently, and as well as the maximum and minimum temperatures. And with the analysis, because this the model, it reconstructs station data for the future generation, the SIM5 data under RCP representative concentration pathway 4.5 and 8.5 emission scenarios were considered in the analysis. That is, these data, the mean future output of SIM5, the average SIM5 for each of the stations were determined under both RCP 4.5 and 8.5. And that was used to generate the future scenarios for each of the stations. And as I said earlier, our climate index was used for the extreme indices, and Mankendo test was used to test the trends and the scene slope as well to determine the direction of the slope of the trend. Now, Sutcliffe efficiency and percent bias were employed to evaluate the performance of the model. These were the two matrices used to evaluate the scale of the model in simulating extreme indices in the basin. And for the Nash-Sutcliffe efficiency, according to literature, it should be acceptable when the result is between 0 to 1. And for the p-bias, the optimal is 0. The smaller, the better. And the positive result meant underestimation of the model, and negative showed overestimation. These were the parameters. Out of the 27 extreme indices, of the earlier extreme indices, 19 were used. 10 were rainfall indices, as shown here, and 9 were temperature extreme indices, as displayed. According to the results, rainfall indices generally were not significant. The trend of rainfall indices were not generally significant over the steady area, although there were more of positive trend, that is using the average and the maximum of the stations, positive trend for total precipitation and the maximum amount of rainfall as the 95th percentile and the 99th percentile, and the 10 millimeter rainfall amount of rainfall I observed in 1 day as well as 5 days, but majorly they were not significant. Compared to temperature, temperature was very significant, generally significant, especially for the warm days, warm nights, cool days, and the cold nights. They were significant, and the trend for warm days and warm nights, they were increasing, whilst that of the cool days and cool nights were decreasing. This shows that minimum temperature is increasing faster than maximum temperature. Maximum temperature, yes. And assessing the performance of the model in the basin, the results show that the model was very poor in simulating rainfall indices. This for the first 4 stations, very poor in simulating the rainfall indices, and this is the last 3 stations for the basin. And when it comes to temperature, the model was moderately skillful in simulating the warm days, cool days, and cool nights. Only 1 station was within an acceptable range for warm nights. So, and as well as the annual temperature, that's the difference between the maximum and minimum temperature changes. It was significant and acceptable across the stations. So these are the remaining 3 stations. The image, the figure here shows the trend of the simulated historical temperature, rainfall, as well as the maximum and minimum rainfall. The model was able to simulate temperature very well, whilst the difference between rainfall, this is a simulated rainfall, and this is the observed rainfall, was very high. It overestimated rainfall, whilst temperature was okay or acceptable. And this has been verified in other studies in the basin. And for the future trend of extreme temperature indices, as the objective of the research was to look at which of the indices is the model able to simulate. And the ones that the model is capable, we look at the future trends. And according to the results, warm days, yes, warm days is increasing, and there's a trend of warm days, the percentage of days that warm temperature was beyond the 90th percentile. In future, from 2011 to 2020, the trend was very similar for both RCP 4.5 and RCP 8.5 scenario, except for the last 30 years of the assessed period, that from 2071 to 2100, that the difference between the RCP 4.5 and RCP 8.5 were quite visible, obvious. You could see the differences from even the plot. But this, and also for cool days, cool days, the trend is decreasing. There's a decreasing trend for cool days. But as earlier seen in the warm days, the difference between the RCPs is only seen in the latter part of the century, from 2071 to 2100, which means that although there could be differences in the mean projections under these two scenarios, that's the business as usual RCP 8.5 and the mitigation option, visible according to the model in the latter part of the century. The result is also similar for the cool night, the last part of the century is also showing the little difference. Whilst although the trend is decreasing across the century, it's only the latter part that we see the difference between the scenarios. And this for the diurnal temperature. For the diurnal temperature, the difference is quite visible in the latter part of the century, although from 2011 to 2040 and 2041 to 2070, you could see that the RCP 8.5 is higher than that of the RCP 4.5. But at the latter part of the century, it is RCP 8.5 showed a decreasing trend, and 4.5 also showed a decreasing trend. But the result, the extreme of RCP 4.5 was higher compared to that of 8.5. This is the trend, projected trend of the mean or average rainfall, maximum and minimum temperature over the basin from 2011 to 2000. And you could see the differences, especially in the minimum temperature. The differences from 2041 to 2000. Maximum temperature kept increasing. That RCP 8.5, RCP 8.5, that's a business as usual, increased. Minimum temperature increase was higher under the RCP 8.5 scenario compared with RCP 4.5. But this was not visible or obvious in the extreme indices. Similarly, for the maximum temperatures, RCP 8.5 increased in the middle of the projected period, and from 2041 to 2070, whilst that of 2011 to 2040 and 2071 to 2000 was almost the same. And this was not visible in the impact of extreme climate indices. Similarly, for the rainfall, RCP 8.5 showed a decreasing rainfall trend, whilst RCP 8.5 had a higher rainfall amount compared to that of RCP 8.5. But in essence, in conclusion, this was not seen. It was not obvious in the impact on extreme climate indices. And although the trend of observed rainfall and temperature patterns shows the potential for more flood occurrence and drought in the basin, the projected model under both the RCP 4.5 and 8.5 was not evidence in the future projection. And this could be as a result of the moderate ability of the SDSM, statistical downscaling model, to simulate temperature and rainfall in the basin. As for extreme rainfall, the simulation was very poor, and temperature, it was okay. But comparing the trends of maximum and minimum temperature and the differences under the various scenarios to that of the extreme indices, we could conclude that the scenarios in the basin, the model in the basin could not capture extensively the impact of the emission scenarios in the extreme climate event. And this could be as a result of the inability of the model, that's the statistical model, to capture the effect of some of the features in the basin. This basin has the largest natural lake in West Africa. The largest natural lake in West Africa is located in the basin. There are also some mountains, like the Green Mountains, in the basin. And the inability of the model to capture rainfall could be as a result of these features. And this could be looked into to improve upon the model's ability in capturing local features, for the simulation of both rainfall and temperature. As well known that rainfall varies spatially, although temperature, the variation is not that much seen. Because of these features that contribute to rainfall formation in the area, the model's ability was poor. And the projected variation in mean temperature and rainfall under these scenarios did not show, as earlier concluded, did not show in the indices. And this called for further studies to see what was actually the problem. Is it because of the features in the basin, or other models are also having similar results? And for policy purposes, there is a need to increase investment in the energy sector to ensure regular supply of power, considering the historical trend of temperature indices, which is currently increasing the heat stress and warm night in the basin. Currently, the basin is recording heat-related diseases. The heat-related diseases are increasing in the basin, and this could be attributed to the trend of extreme temperature indices. And power in the area, which could have averted some of these temperature stresses, especially in the night, is not stable. It's not stable, and investment in that line could help reduce the impact of climate change on these heat-related diseases in the basin. More also, there is a need to invest in early warning systems and disaster management. As earlier said, the trend of rainfall is showing more frequent floods and drought. And most of the farmers, as a form of an adaptation, are now moving closer to the river bodies to have access to both surface water and a very conducive climate for the activities. And without these early warning systems, most of the farmers are losing their field to floods, as well as their livelihood and their habitation. So investment in this line would help. And also, policy should help protect the forest. Currently, there is this illegal mining activities in the area that is degrading the forest and competing with farmers for suitable land for their activities. When policy focus on the protection of these forests, it will help regulate the local climate and reduce even the expenditure of the farmers. For example, if the climate is conducive, the local climate is conducive, it will help reduce the warm temperatures, warm night temperatures, and the amount of energy needed to regulate these in the night will reduce. So these are policy recommendations that are proposed from the work, And for future research, investigation into the component of the atmospheric systems responsible for these changes, that's the extreme rainfall and temperature changes, should be investigated. Thank you.